Monday here at noon, there's going to be a pro-section student that's going to help out with a kind of a tutoring session for you. In case you're interested in coming here Monday at noon, we'll have a little bit of a review by the pro-section student of material on the upcoming exam. So it is open to you. If you can't make it, that's fine. If you're interested, somebody will be here for that if you'd like to come. With that, yes.
How long is that going to be?
Noon to 1.
Okay.
Extra credit?
You guys have more extra credit opportunities than most classes do. So don't push your luck.
Don't push the main.
That's what.
Gotcha.
All right. The last part of the adrenal gland is the adrenal medulla, and that is responsible for releasing catecholamines into the bloodstream. 75% of those catecholamines are epinephrine and 25% are norepinephrine. Epinephrine has a great impact on the heart. You know, whenever you see some of those Pulp Fiction movies and stuff like that, and they stab the heart with this big syringe and push a bunch of drugs into it, it's epinephrine that they're actually injecting into the heart because it has a increased heart rate activity as well as increased force of contraction. Also, epinephrine increases overall general metabolic functioning, so makes cells more efficient and more active in their activities. I think I'm starting to get Liz's cold. This is not a good sign. Norepinephrine is a very potent vasoconstrictor, and so if there's any sort of hemorrhaging or something at all like that going on, vasoconstriction is a very helpful phenomenon that norepinephrine can provide. Let's go ahead and take a look at the next endocrine tissue or organ, because the pancreas is endocrine and exocrine. And everybody pretty much knows the endocrine portion of the pancreas is the production of insulin. But there's another hormone that's being produced, and that's called glucagon, and it has similar properties to insulin, other than its differences, it's kind of opposite to what insulin does. Let's take a look at this picture here first of the pancreas and realize that the surrounding tissue is called acinar tissue. So collections like this are all related to the acinar aspect of the pancreas, and so in your histology drawings for yourself, make sure that you correctly identify acinar tissue. And you know, it's a little round circle with these cells that are all coming, so to speak, in a circular pattern with a nucleus off to the perimeter. So that's the acinar tissue. However, the islet of Langerhans, or the pancreatic islets, are embedded throughout the pancreas in the overall acinar background. And so they have a fairly good size. They're going to definitely be larger than the acinar tissue themselves, and are going to be composed predominantly of cells that are going to be our beta cells, which are the cells responsible for the production of insulin. There's other cells in these islets. Those are the alpha cells, and they're the ones that are going to be responsible for the production of glucagon. And we'll get to that in our notes in just a little bit. But when you make your drawings, you just have to make them to where you can recognize the tissue that you're looking at. And so make sure you put in landmarks that actually work for you. This is a special stain, and this special stain is designed to actually give you a better idea of what cell type do you think. This is going to help us get a better view of our alpha cells, and the alpha cells in this stain are less frequent than our beta cells, and so those are these cells here that are actually taking up this kind of reddish aspect to the stain itself. So those are examples of the alpha cells, and you can tell that they are not the predominant cell type of these pancreatic islets. So let's go to the written material about the pancreas and its islets. Alpha cells. Alpha cells are the ones that are red in this stain. Their cytoplasm is red. They release the hormone called glucagon, which is designed to increase blood glucose. The target for glucagon is primarily the liver. And Liver is able to actually store glucose in the form of glycogen, and so hence glucagon and glycogen are very similar in their sounds. So glucagon is primarily targeting the liver to break down the storage form of glucose, which is glycogen, into glucose molecules to release it into the bloodstream. Now, why would we want to have glucose dumped into our bloodstream? Well, we haven't been eating for a while, right? And when do we not eat for a while? It's when we sleep. And so the liver is taking care of us and allowing us to have a nice homeostatic level of blood glucose throughout the night when we sleep. So that's typically when glucagon is actually being released during our overnight fasts. The beta cells, on the other hand, are the cells that are producing insulin, and insulin has the opposite effect of glucagon. It's designed to decrease blood glucose. And insulin essentially targets almost all body cells. It is a 51 amino acid protein. So it doesn't need a carrier molecule to actually circulate around in the bloodstream. And it is required for glucose entry into the cell. So can glucose get into your cell without insulin? No. And so that's our problem, and that's what we're going to actually come up to in just a moment. What is the feedback mechanism for both of these systems? Negative. So when blood glucose goes up, what happens to glucagon levels? They go down, and when insulin's high, but because glucose is high, then glucose goes down and insulin goes down. So both of these are negative feedback. Now, diabetes mellitus is such a common problem in our society, and it's getting to be more and more prevalent. And it's related to the second diabetes that we're going to talk about, which is often referred to as adult onset diabetes mellitus. And it is predominantly due to the problem of eating too much in our culture. So it's due to a very excessive caloric intake for individuals without the appropriate caloric expenditure for people. So in other words, it comes with being overweight and sedentary for type 2 diabetes. Let's talk about the type 1 first and then go into some of the reasons that type 2 is so commonly seen with people who are obese and sedentary. Type 1 is referred to as insulin-dependent diabetes mellitus. It used to be in the literature IDDM, insulin-dependent diabetes mellitus. It was also called juvenile onset diabetes because we actually acquired this diabetes because we acquired an autoimmunity to our beta cells. When you hear the term autoimmunity to beta cells, what does that mean to you about the health and survival of beta cells? Yeah, we off them. So they're our own cells. We should be able to recognize them, but through typically a viral process, we have suddenly decided that they aren't belonging to us anymore, and we're going to take them out because they are now in our immune system's mind foreign material. Well, when you take out the cells that are responsible for producing insulin, what happens to your insulin levels? They tank. And so these people ultimately have zero insulin. Well, what does that mean about their blood glucose levels? Really, really high, because you need insulin to take it out of the bloodstream to put it into the cells. So without the insulin, the sugar, blood glucose, continues to circulate and increase and increase and increase, because your body is telling all of your other parts of your body, I'm starving to death. Your cells are saying, I'm starving to death. So people who have this problem, they don't have to eat for their sugars to go up. Their sugars will go up because the body is sending signals to other portions of the body responsible for helping it to get sugar, causing it to dump more sugar into the system, because the cells are saying, I'm starving, feed me. Well, to the body, it's give me more glucose, which means put more glucose in the bloodstream, so their levels go up, and they don't even have to have anything to eat, because their body starts eating themselves, breaking things down and putting it into that. So what happens here, again, glucose is unavailable to our cells. So we must feed these cells, and the body will break down fatty acids FAs for fatty acids. Do you guys remember what major molecule has a bunch of fatty acid chains attached to it? Triglycerides. So, and triglycerides are put into our fat cells. So now our fat cells are being told to release triglycerides. So they're putting triglycerides into the bloodstream, and the fatty acids will be taken off and entered into the cells so that the cells can use the fatty acid for a fuel. Well, if the body's breaking down using triglycerides, the fatty acids from triglycerides for fuel, this causes our blood to become lipemic. Lipemic lipid. So our blood literally gets creamier. You know how we have the different kinds of fats in our milk? You know, skim milk, 1%, 2%, 3%, and more. This is what we're doing. We're creating a situation where we're getting more and more fats into the blood, and actually you can see in people who have this problem and they set their blood tube out and just let it set in the tube rack, you will see a fatty layer actually start to accumulate on the top. And so that's that lipemic situation. Plus, cholesterol is elevated. All of these, very bad for your blood vessels and for overall health. Because we're using fatty acids from triglycerides, we will obtain fatty acid metabolites. The fatty acid metabolites that are accumulating end up being byproducts called ketones. The more ketones we get, the ketones have an acidotic aspect to them, and so we get ketoacidosis. And ketoacidosis is actually a life-threatening condition which will cause the person to essentially die. pH is dropping, ketones are high, and all other metabolic disorders are occurring, and we'll talk about that with general adaptation syndrome at the end of this chapter, because I like my spelling. I definitely am not feeling well today. Metabolites look awful. At least I'm noticing afterwards. Okay, fatty acid metabolites. And so this ketoacidosis actually can cause ultimate demise of the individual. And That's what we're going to talk about with cellular exhaustion, which is at the end of this chapter. Well, the only way to fix this is by injecting a genetically engineered insulin. And you get genetically engineered from GMOs, genetically modified organisms. So what they've been able to do is they've been able to take a bacteria, which bacteria can rapidly multiply and make byproducts, and they've inserted the human insulin gene into bacteria. And so the bacteria are making human insulin. In the past, before we had this ability to genetically modify our organisms for our benefit, the only form of insulin that people could get was insulin from pigs and cows. So they would actually harvest insulin from those animals and concentrate it and then give it to people in an injection format. The problem is insulin from pigs and cows is not the 51 amino acid insulin from us. And so ultimately, those people will actually develop resistance and an immune response to that insulin, which means then they have to have more and more and more insulin because there's less and less insulin that's actually working for them. So our genetically engineered organisms, which are giving us human insulin, will allow us to actually accept that insulin and not know it as anything else but ours. And so that's how you treat type 1 diabetes, with genetically modified insulin or engineered insulin. Type 2 diabetes is very different from type 1 diabetes. It's called non-insulin dependent diabetes mellitus, or NIDDM. You may have seen some of these in the literature. Also, adult onset diabetes, because obesity was more commonly an issue for adults, but no longer is that the case, unfortunately. Now in the literature, I see it actually abbreviated T for type 2D, type 2 diabetes. That's the more common abbreviation in the literature these days. Now, this one's very different. This one says non-insulin dependent diabetes. And this is because our insulin receptors sensitivity is messed up. And when I say it's messed up or altered, it is less sensitive. So what does that mean if you want to get glucose into the cells? You're needing more insulin. So our insulin receptors are less sensitive, which means that it's getting harder to get the glucose into the cells because we are having some glucose entry into the cells, but not like what we should have. So what happens to our insulin levels if we're a type 2 diabetic? They go up. And what happens to our blood glucose levels? They go up. So this is different, isn't it? Type 1, insulin is on the floor. Glucose is at the ceiling. Type 2, insulin is up and glucose is up because our receptor sensitivity is all messed up. What's interesting about this, the receptor sensitivity that is messed up is predominantly due to adipocytes. So adipose cells are actually producing a chemical that decreases insulin sensitivity. You can kind of liken it to like a blocker. It's blocking insulin from actually landing on that receptor and allowing the cell then to take in glucose. So our adipocytes are producing a chemical that is interfering with insulin's ability to act on you and help bring glucose into the cell. So in this situation, we really don't get ketosis. It's not a problem initially. It can, or usually. You know how you say there's always exceptions to the rules, and there is indeed exceptions to this rule. So in order to treat type 2 diabetes, what do most people know is the most common thing that they ask people to do before they start giving them pills? Diet and exercise, and they don't like to say it because people don't like to hear it. Weight loss. Yeah, and that is the treatment for type 2 diabetes. Diet, you can get them to go, okay, I'll go on a diet. Plus exercise, well, you know, depends upon who you're talking to as to whether or not they'll be game for exercise. But weight loss. So we need to get rid of those adipocytes that are releasing those chemicals that are actually inhibiting the ability of insulin to do its job. And so that's the treatment for type 2 diabetes. So elevated glucose, elevated insulin, cells are getting some glucose, but they're not getting enough to make them happy and function properly. Do you guys know what the common symptoms for diabetes is? If somebody has got diabetes and hasn't been yet diagnosed, or thirsty, so that's called polydipsia, that's right. So they're drinking a lot of water. If you drink a lot of water, what else do you do? Polyuria. And you're starving, so therefore polyphagia. So those are the three polys that come along with people who have diabetes. They drink a lot, they pee a lot, and they eat a lot. And the reason they're eating is because their body's telling them, I'm starving, even though the blood sugar's up. Yes?
What happens when to lose like your limbs? Because a lot of people with diabetes, like we have to cut off a limb or something.
Well, right up above, when you don't have the proper metabolites to use for your cellular energy, for your ATP production, you will use fatty acids. If you can't get glucose into you, you will actually use fatty acids as the alternative fuel. And in order to get fatty acids, that means you have to put triglycerides into the bloodstream. And when you put triglycerides into the bloodstream, it also causes cholesterol release into the bloodstream. And all of those things together do what to the inside of your vessels? They clog them up. The smaller the lumen or diameter of the lumen of the vessel, the easier it is to actually clog it up with this sludge. And so therefore, that is why you actually end up with digit loss and limb loss for people with diabetes. This is more common a problem with people who have insulin-dependent diabetes, not so much with type 2 diabetes, where you actually have insulin already in the system. Let's go to the pineal gland and talk about its endocrine aspect. Our notes state that it's a tiny gland hanging from the roof of the third ventricle, but in order to see the pineal gland, where did you guys look on your sheep brain? Yeah, at the back of it, yeah, to, wedge apart the cerebral hemispheres from the cerebellum, and then you were able to see the pineal gland. The pineal gland is responsible for producing a hormone called melatonin, and it is produced by pinealocytes. So those are the cells of the pineal gland. And melatonin is an interesting hormone because the pineal gland is hooked up to our visual pathways. And so light is actually detected by the pineal gland. Whenever we are using our eyes and it's daylight and everything, that light goes to the pineal gland as well as our visual cortex. We'll have a little bit of feed to the pineal gland. And that's interesting because when we receive light to the pineal gland, it will inhibit melatonin production and release. So when we close our eyes at night, what happens to our melatonin production and release? It increases. And so peak levels are at night, and also melatonin levels are higher in the winter times than they are in the summer times. They're lower melatonin is lower in your system in the summer times when you have all that lovely daylight, because that's an important stimulus to the production or lack of production for melatonin. Now, melatonin is interesting because you can buy it over the counter, yes, and people buy it for insomnia. And so what's really nice is melatonin is actually pretty easy to produce over the counter, and many of the over the counter products are actually contain what they say they contain, but not all of them do. So you always have to be very careful with the quality of the product that you get with supplements, because they're not regulated. That's why they have lead and other things in them. But when you take melatonin, it may indeed help you sleep. But does everybody see that have the same response to melatonin? No. So a lot of people's sleep disturbances may benefit from melatonin, but melatonin may not be the reason that they're having their sleeping problem. So everybody's a little different. I tried melatonin one time for jet lag, and it gave me the worst nightmares, and I could never get into a deep sleep. So it was just like, oh, this stuff is horrible. I don't know why people take it. Here, you have it. I don't want it. So, but everybody's still wired a little bit differently. So melatonin can help some people, but other people it doesn't have a beneficial effect for. So remember, when somebody says, oh, this works for me, here, try it, it may not work for the other person that you're actually handing it to. The other interesting thing about melatonin itself, melatonin is kind of anti-gonadotropic. Now, that word should mean something to you. Anti-gonadotropic. It's against your gonads producing their hormone. So it's an interesting phenomenon, because for us, what worked for us as a child, once we had hit adolescence, it doesn't work so well for you often. You can give kids, some kids, you give them Benadryl and they get hyped up. And then after they get through adolescence, the Benadryl doesn't necessarily hype them up anymore. So adolescence causes a lot of changes in how we respond biochemically. And melatonin is anti-gonadotropic more for when we are children. And this is going to help to prevent what's called precocious puberty. Anybody know what I'm trying to say with precocious puberty? Puberty at age 6. Yeah, precocious puberty. So puberty is supposed to be around 11 for girls and 12, 13 for guys type of stuff. So melatonin has an anti-gonadotropic effect for us as we are young. Doesn't necessarily have so much of an anti-gonadotropic effect for us as an adults, but if you take melatonin and you notice you're kind of cranky, maybe you should stop. So thymus. Thymus is also considered an endocrine organ. What's really interesting, thymic hormone, which is what it produces, isn't really so much dumped into the bloodstream as it's actually part of the thymic gland itself to actually work with the cells that it actually is changing for us. So thymic hormone is specific for, makes a certain subset of white blood cells, WBCs for white blood cells, into T cell lymphocytes. So thymic hormone is going to play a very big role in a part of the development of a certain branch of our immune system. And this certain branch of the immune system, because the white blood cells are part of our immune system, called lymphocytes, will actually be trained to be very specific types of lymphocytes called T lymphocytes. Guess where they got the letter T from? Thymus. And so T cells or T lymphocytes, because that's what we typically call them, we call them T cells. T cells or T lymphocytes are very specialized white blood cells of our immune system, and we'll get into that when we get into that chapter. The thymus is largest and most active when we are young. After adolescence, it begins to atrophy. And will turn into just fat plus connective tissue. So there is still some thymic activity, but the big thymic gland just gets smaller and smaller and smaller and smaller and smaller. So it's really big in newborns and infants and toddlers and everything, because when they're born, they're exposed to this world. And this world is full of things that we need protection from. So the thymic gland is really super duper active when you're young. Then after puberty hits, it's done its main job of getting everything set up for your immune system. Then it starts to actually atrophy and get smaller, which also seems to coincide with a problem as we age. Because as we age, we become more susceptible to cancers. And so cancers are also a manifestation of a breakdown of our immune system. So it's a very interesting correlation to that.
So when children have cancer, is that?
When children have cancer, their thymus wasn't doing its job for them very well at all, indeed. The thymus is deep to our sternum, so it's between our sternum and our heart, and the superior portion of our heart. Now let's get into what I was alluding to earlier when I was talking about ketoacidosis, a phenomenon called general adaptation syndrome, GAS for short. It is indeed the opposite of homeostasis. It is trying to save your life. So general adaptation syndrome is a life-saving mechanism that your body is going to employ, because ketoacidosis will trigger general adaptation syndrome. Our terms here, eustress, true stress. It is actually very true. Stress is good for you. You undergo stress every day. You get out of bed, your body's experiencing stress, you know? So all kinds of things that you do are various manifestations of stress. And throughout the day, you know, the stress level goes up and goes down, goes up and goes down. But that's normal, that your body's geared for that type of stress. Even taking evals or taking A&P exams are still a eustress. Sometimes doesn't feel like it, but it is. It is not a distress which will actually initiate the general adaptation syndrome. Distress is destructive. It's harmful and it lowers your immune response. So we're getting failure to survive with true distress. And so let's go a little bit more into the various stressors that can cause or trigger this general adaptation syndrome. And our notes have in parentheses bacteria, bleeding, and emotions. A stress that initiates general adaptation syndrome is what we're referring to. And when I say bacteria, I'm talking about bad case of pneumonia. I'm talking about meningitis. I'm talking about bacteremia or sepsis. So I'm talking about bacteria where they should not be in you. And it's taking you down. Bleeding. I'm not talking about you cut your finger. I'm talking about you cut your arm off. And so you're hemorrhaging. And so that's what's going to initiate the general adaptation syndrome. So therefore, when I talk about emotions, that's what I'm telling you. That bad grade that you got on the A&P exam is still not enough. I'm talking about you lost your child. I'm talking about you lost your spouse. I'm talking about those emotional stressors that people sometimes do not ever recover from, because actually that general adaptation syndrome was what they decided to succumb to so that they could follow them. Because you hear about people that not long after they left this world, and this was actually a process that was initiated in them, and they decided they didn't want to fight it. So human beings are interesting things. Their reasons for living are quite individual. Let's take a look at what will cause somebody to succumb to something such as severe emotions and loss of a loved one, or ketoacidosis. So a stressor is happening, such as ketoacidosis is developing. This is felt by the hypothalamus. That hypothalamus is not a very big area, but it does a lot for us. The hypothalamus will turn on the general adaptation syndrome through two pathways, because the hypothalamus is part of two things, isn't it? Part of the nervous system and part of the endocrine system. So that's what that's why we talk about this here. This hypothalamus will say, I'm going to turn on a nervous system mechanism, and I'm going to turn on an endocrine system mechanism. Which one's going to be felt by you first? Nervous system. And when that fatigues, which one's going to take up the slack? The endocrine system. So as the hypothalamus, you'll turn them both on at the same time. However, you won't feel the second one, which is endocrine related, and it's called the resistance reaction. The nervous system reaction is called the alarm reaction. So like an alarm, you reach over and you have an immediate response to it. That's going to be nervous system initiated, and there's a certain brand of the nervous system that takes care of us whenever there's a bad thing happening. Sympathetic nervous system, fight, flight, will be turned on. And so in our notes we have here, alarm reaction. That's turned on as well as the resistance reaction at the same time, but we feel the alarm reaction first because it's a right-of-way impact. We have the sympathetic nervous system stimulating our body, as well as, because we actually talked about the neural connection to the adrenal medulla, and we are going to also tell the adrenal medulla to release epinephrine, norepinephrine into the bloodstream, which will, you'll feel it a lot sooner than you will the other parts of the resistance reaction. So the alarm reaction is the initial reaction felt to the stressor. It is indeed fight, flight, activated by the nervous system. It's sympathetic in its activation, and these activities are designed to counteract immediate danger. So you have to realize these are generic responses. And so we said bacteria, bleeding, and emotions. This will all initiate this very generic life-saving response designed to counteract that immediate danger. Well, we all know these are quick to start. That's why we notice them. But fatigable. So this fatigues, therefore, is short-lived. When the alarm reaction is working and doing its thing, you'll notice it has very significant effects on these organs here. The heart. What do you suppose the heart will do when it's getting its alarm reaction? Okay. It increases heart rate and contractile efficiency. So it's putting out a large amount of stroke volume. The brain will get vasodilation. Why do we want to vasodilate blood vessels to the brain? We're trying to figure out how to get out of here. We're trying to use our brain to figure out what we can do to take care of ourselves. Do you think the heart's also going to have blood vessels to it vasodilate? Absolutely. Skeletal muscle, because this is an alarm reaction, this is an immediate danger. What do you think will happen to the blood vessels of the skeletal muscles, especially of your legs? They will vasodilate, absolutely. What about the lungs? What about the blood vessels to the lungs? They will open up, and even your respiratory efficiency will increase. Respiratory rates going up, respiratory gas exchange is improving, all that kind of stuff. What about blood vessels to your skin? Yeah, your body actually thinks you can live without it. So we will get vasoconstriction. So people who have a heart attack often appear pale. Urinary system. Who cares if you make pee, right? We're going to vasoconstrict. Digestive system. These are the digestive processes of food. We're going to vasoconstrict, and we'll get dry mouth. We'll get all of those things where you're not actually going to be using those fluids in those areas. So again, vasoconstriction. And decrease of any digestive process. Spleen. The spleen is an interesting organ. We'll talk about it more in detail when we do the immune system. The spleen's like a bag of blood, and it actually has a little bit of capacity to contract, and so it gives you a little blood bolus. And so that's what that's about. Forces extra blood into the general circulation. The liver, remember, it has typically a lot of glycogen, which is a storage form of glucose, and it will start chopping that glycogen up into glucose and start pouring it into the bloodstream because everything's revved up, right? And if everything's revved up, you need fuel for all that stuff that's actually revved up. The adrenal medulla is going to be stimulated by the hypothalamus to actually release its epinephrine and norepinephrine. So E/NE release to augment this response, or responses, these. So this is trying to get you immediately away from what is perceived as a life-threatening event in the normal mobility way. But you can have sepsis, and you can have diabetic ketoacidosis, and you don't really need to run away, but the body still turns on this mechanism for you. Now, if the alarm reaction isn't going to be enough to take care of you, such as in ketoacidosis, then the resistance reaction will then be felt, okay? And the hypothalamus is going to tell the anterior pituitary and the adrenal cortex to do some stuff. It's going to tell it to release hormones. And so the hypothalamus will have a big release of hormones from the anterior pituitary as well as the adrenal cortex. And this reaction is slow to start because it takes time for these hormonal control mechanisms to actually get initiated. The resistance reaction will help us fight the stressor long after the alarm reaction has fatigued. These are the three main hormones that are going to be released from the hypothalamus to our anterior pituitary, and also from the anterior pituitary off to the adrenal cortex. CRH, corticotropin releasing hormone, that's from our hypothalamus. It will act on the anterior pituitary to cause it to release adrenocorticotropic hormone, which is really fascinating because under ordinary circumstances, ACTH will not affect the release of aldosterone under ordinary circumstances. So in this situation, ACTH actually does cause a very big release of aldosterone. So remember, ACTH does not usually cause aldosterone release. But in this case, because of the amount of CRH that's being released and then the amount of ACTH that's being released, aldosterone is then being told you are going to be released because all of the adrenal cortex is going to be releasing their hormones, not just aldosterone. We'll have glucocorticoids being released and gonadotropins being released, but those gonadotropins are not going to cause any sort of major hormonal effect other than trying to actually cause the muscle tissue to also respond. So ACTH is going to now affect aldosterone release. This is going to cause your kidneys to take sodium and retain it. So uptake of sodium means retention of sodium to maintain our fluid balance, because what always follows sodium? Water. So we're going to take up sodium because we want to keep as much water in our system as possible because we're going to need this because who knows, we might be dehydrating soon. Okay? And to do this, we have to get rid of potassium. This process demands potassium go into the urine to be peed out and leave your body, and sodium be taken in and water be taken in. So this is a very key process and problem right here. Thyrotropin releasing hormone will stimulate the anterior pituitary to release thyroid stimulating hormone, because you can see all the time it takes for all this to work, to then cause the thyroid gland to release thyroid hormone. Thyroid hormone is released because we want to increase carbohydrate catabolism. Catabolism means to break down. So we want to break down our carbohydrates so that we have more fuel for this danger that we're fighting, and all these organs are functioning super duper optimally and even above beyond. Growth hormone releasing hormone is also released by the anterior pituitary to cause the release of growth hormone, which interestingly increases fat catabolism. Both of these are fuel reasons. Okay? We need the fuel for this life-threatening situation. So think of somebody who has diabetic ketoacidosis. Has anybody ever been around somebody that's had diabetic ketoacidosis? You know, they're typically not a fat person. They're typically on the skinny or slender side. And that's because we have lost body fat because of this resistance reaction. So we've lost body fat because we're trying to fuel our cellular processes. Okay? And that's why in our notes here it says due to energy demands. And also, if they're in DKA, are they having a normal respiratory rate? They're huffing and they're puffing. Not really obvious like somebody with emphysema, but they have a very rapid respiratory rate. What about their pulse? It's fast and thready, because no matter how much fluid they take in, they can't take in enough to take care of their body demands. And so you can take that person and you can put the 2 full bags of IV fluids in them and just think like, oh my God, they're going to go into heart failure. No, they are so dry that you're just starting to actually do something for them. And the reason they're so dry is what's in your breath, people? How does your mouth feel if you have a head cold and you had to sleep all night long with your mouth open? Dry. So that rapid respiratory rate has consequences to it. It's not just that they may be peeing a lot, because they are actually peeing a lot. If they actually went into diabetic ketoacidosis, they were peeing a lot before this happened. But they're breathing a lot and they're peeing a lot. One of the reasons that they're peeing a lot, and I'll explain it now, and we'll get into it again when we get into the renal system, is that they're peeing out. The reason they have polyuria is because they have a lot of sugar in their urine. The old-fashioned days, you know how they found out somebody was a diabetic? They tasted their urine. I'm going, how gross is that?
Yeah.
Other cultures still drink other people's urine, though. I'm just going, this is just, I'm glad I'm not that culture. That's all I can tell you.
But it's sterile.
Well, it's sterile until it hit the output, final output area. So they have sugar in their urine. Sugar is osmotically active. Are you guys starting to follow me with that? What is osmosis? Water always follows particles. So the reason they have polyuria is because they have so much sugar in their system that their kidneys can't eat, has to get rid of it. It dumps it out. Well, if the kidneys are dumping sugar into the urine, water follows. And so that's one of the main reasons why they actually have polyuria, is because they have super duper concentrated urine, which needs to be diluted out by water. So in DKA, they're skinny, they've lost body fat because they've been actually breaking it down, trying to feed the cells with fatty acid metabolites. They are also in ketoacidosis, so they have a lot of hydrogen ions floating around in their bloodstream. But the thing that will kill them is this. Because aldosterone said, put potassium in that urine with that glucose, for example, in diabetic ketoacidosis. Well, you guys have to realize your blood potassium level is never very high. I always remember 4. Potassium is supposed to be 4. Sodium is supposed to be 140. I like numbers that are easy to remember. So if you're peeing out a bunch of potassium, is your blood potassium level 4 anymore? No, it's starting to go down. And you can't tolerate much fluctuation in blood potassium levels. So as it goes down, your cells are going to try and save you, because the cells like you. They're going to try and save you. And they will take and where's potassium? Why are cells going to save you? Because what's high inside a cell? Potassium. So potassium in the cell will go, okay, I'm going to give you my potassium, because if I don't give you my potassium, we aren't going to depolarize and repolarize very well anymore. So the cells start donating their potassium to the bloodstream. Well, what does that mean about the cell's potassium levels? They're dropping down, which if you start losing potassium, what does that do to the cell's ability for its resting membrane potential? Right? Doesn't it go down more and more and more negative? Which is kind of counterproductive if you're trying to do this depolarization, repolarization thing. So the cells are losing potassium, and so in order for them to get the proper resting membrane potential, you have to put another positive ion inside. And what do you have floating around that's a positive ion in your bloodstream if you have diabetic ketoacidosis? It's called protons, right? A hydrogen ion. And what do we know about a whole bunch of protons? That's called acid. So your cells are trying to save you and artificially elevate your potassium level so that you can function. But in order for the cells to function, they have to be then another positive charge put inside them, so the hydrogen ion goes inside them. The cells also are having major fluid shifts because you're losing fluid, and what are your cells made out of? A bunch of fluid. So the fluid from the cells gets lost into the bloodstream, the potassium from the cells gets lost into the bloodstream, and the hydrogen ions or protons from the bloodstream gets dumped into your cells. Is this going to make a happy, healthy cell? No. And that's cellular exhaustion. So that's exhaustion on a microscopic level, which will have its major impact macroscopically on your body. And so when you check, when somebody comes in with diabetic ketoacidosis, they want to know what's that person's potassium level right off the bat. Because they know as soon as I start pouring fluids into you, what does that mean to the potassium level, that whatever it was at the beginning? Ooh, boom, it's going to really start tanking. So the potassium levels are going to tank and your total body potassium depleted. Total body potassium depleted. So before they even give you insulin, they want to give you actually potassium. Because they will give you the fluids and they will give you the potassium and then they will give you the insulin. Because if they give you the insulin before they give you the potassium, they actually make it worse. And so it can cause the actual demise of the individual. So in the notes here, a little bit. Cells then lose intracellular potassium to replace the lost extracellular potassium. Hydrogen ions will flow or go into the cell, acidifying the cell. Water from the cell is lost or let go into your vascular circulatory system. Because you need to have adequate circulation in order to survive this and get the proper ions and nutrients and all that good stuff to you. And so now you have an acidified, dehydrated cell with total body potassium deficiency. And that's what exhaustion is all about. Exhaustion isn't how we feel at the end of the day. This is cellular exhaustion. This is exhaustion on the microscopic level, which leads to macroscopic, overwhelming total body collapse. So alarm reactions and resistance reaction turned on at the same time. You feel the alarm reaction first because it's nervous system initiated, sympathetic nervous system. The resistance reaction is taking its time because it has to circulate. All these regulating factors have to be released and all that stuff. And then it starts to work for you. But if you don't correct the underlying problem, the body overshoots it. Can you guys follow me with this process? The body is overshooting it because it thinks you're dying, and because it thinks you're dying, it's throwing everything in to try and save you. But in doing so, it will ultimately cause your demise if you don't intervene. And so it's the proper intervention that actually goes ahead and stops all of these processes from happening. But you have to realize when somebody comes in and they've been severely stressed, they've lost fat, and you can tell this. They've lost the body fat, and they're having a rapid respiratory rate, rapid heart rate, and thready heart rate. And with diabetic ketoacidosis, you can actually even smell. They smell very different. Their skin smells, their breath smells very, very different from a normal individual. And so you have to treat them as if they are going to die any minute, because they actually could do that in front of you any minute. So that's the resistance reaction. It only happens if these two are failed to be corrected, the alarm and the resistance reaction. If they fail to be corrected, then exhaustion will actually be the ultimate outcome.
Why is it when some people experience the fight or flight, sometimes they have a sympathetic nervous system, why is it that they urinate and freeze up? It seems counterproductive to survive.
Urinate and freeze up. Well, there's a lot of theories about that. Part of the reason for urinate is they lost sphincter control. Yeah, and so they voluntarily lost sphincter control. That wasn't on their mind, is part of that. So that's part of the urination and sometimes the defecation. That wasn't on their mind, trying to control those sphincters. And freezing up, some people hypothesize, because this is just a hypothesis, that it's like when deer stop when you're hunting them. They're hoping that they blend into the background. And so it's kind of that type of thing. That's the theory, you know, and if you think about it, you know, you can kind of see that, you know.
Yeah. Even talk about like camouflage.
Yeah, they don't camouflage well at all. They have to depend upon their clothing for any sort of camouflage. So that's the end of the material for our first exam. So special senses and endocrine system. One of the things that's always helpful is if you guys will actually take time and try and start with a certain amount of information from a global aspect, and then see how many details you can hang on to that information, and how much you can go into an actual area with a lot of detail. Because with the hormone system, remember there's two main categories of hormones, right? Amino acid-based and steroid-based hormones. Amino acid-based hormones are water-soluble, so you don't have to worry about having something to move it around in the bloodstream, whereas steroid-based hormones are hydrophobic or lipophilic, and so you have to have a carrier protein to move them around in the bloodstream. Also, because of their different construction, they will actually have different effects on their target cells. Steroid hormones can move all the way through the cell and ultimately bind a receptor inside the cell, which will then go into the nucleus and activate a gene to make maybe insulin or something like that, or like if it was testosterone, to make more muscle fibers, for example. And your amino acid-based proteins have to depend upon landing on a surface receptor and activating a cascade of events where the hormone is the first brain fart. Let's go up in the first messenger. That's right. I'm going. First messenger, and cyclic AMP is the next big important messenger. But remember the steps or the sequence involved in that, from the hormone to cyclic AMP, and then also remember cyclic AMP is going to activate or deactivate various kinases inside the cell. So there's a lot. If you start with the big picture and then start working on them individually and coming up with details, it does help, because as you talk about this to somebody else, then they can say, whoa, you got that wrong. I don't think that's right. Let's look it up. And testing yourself via that method is actually a very good way to actually encourage the learning experience. In chapter 18, this is all about blood. I love blood. Blood's called go-go juice, because when you don't have enough of it, you don't feel like going. But when you have enough of it, especially if somebody's been anemic to the degree where they require a blood transfusion, you put some blood in them, they go, I feel so good. You know, I didn't know I was that tired. You know, so blood is a very important unit that helps us to provide the oxygen to our cells so that we can actually function optimally. Because that's what it is. But our red blood cells are basically bags of hemoglobin that are designed to actually deliver oxygen to our cells. And then we need to take carbon dioxide away and put out an off gas in the environment and put more oxygen in. And so the cycle goes on and on and on. Taking a look at the composition of blood, because you guys have done this with that Phil's or Learn Smart Lab stuff. So they were talking about that and talking about how to centrifuge, and those little centrifuge experiments are always interesting because it always has to be balanced. So many of you actually learned, if you don't balance your centrifuge, you don't get a good result. And so if you put one thing on one side, you got to have another one on the other side. And I thought that was pretty snarky of them to actually give you 5 tubes, And because I'm going, I wonder how many students don't realize that we need to have 6. So one of these you had to double up in order to actually do it. So, but if you didn't realize it, you learned about it as you were doing the experiment.
Again and again.
Yeah. So we do a lot of testing of blood because blood tells us a lot about a person's well-being. We can get a lot of information from it. And this picture here shows us the basic components of blood after it's been centrifuged. Because when the blood tube comes out, it's this nice red fluid sitting in this tube. And it's got some viscosity or thickness to it, and that's due to what's called albumin. But the bulk of blood is plasma. Okay, that's the fluid portion of our blood. 55% of our blood is from plasma or fluid. Then less than 1% of our blood, which they call the buffy coat, is due to white blood cells or cells of our immune system. So less than 1% of our blood contains cells of our immune system, and yet we're still doing actually quite well. And then the next largest component of our blood, but at the bottom of the tube, because it's so heavy, are erythrocytes, are our red blood cells. And so these are the guys that are responsible, though, for carrying oxygen around in our bloodstream. So these are the ones that are really important for making us feel like we can get up and go when we have adequate oxygenation to various tissues. Our notes here talk about components of blood. Formed elements, cells and platelets, red blood cells, white blood cells, and platelets, and then the plasma, which is the non-living viscous or slimy fluid part of our blood. That viscous nature is due to albumin. We actually have albumin in our blood. It's about 8% of our blood, of the proteins in our blood, albumin. So that's what gives our plasma, our blood, a little bit of sliminess. Blood has a very narrow pH range, 7.35 to 7.45. And remember I told you like the 4s? Potassium's 4, sodium's 140, blood pH is 7.4. C4s work really, really well. So keep that in mind. So a normal blood pH is actually, in my mind, 7.4. And that's what most people, if you ask them what's a normal human's blood pH, is 7.4. So the fluctuation to 7.35 to 7.45 is not very large fluctuation at all. We do not tolerate going down below 7.35 or going above 7.45 very well. Is this 7.4 a neutral pH in a chemistry lab? No, but it is our neutral pH. So 7.25 in a chemistry lab, it would be basic, but in us, that's acidosis. So anything below 7.35 is acidotic. Anything above 7.45 is alkalotic or basic. That's for us. We're the center of the world. And so everything that's important in this world centers around 7.4. Men have about 5 to 6 liters of blood in them. That's all of the plasma, the buffy coat, and the red blood cells. 5 to 6 liters in men. So that's, 2-liter pop bottles, bring about 3 of them out and pour them into a guy, and that's what you got. Women have about 1 liter less. So just 2 liter bottles. Pour them into her, and you got the volume of a girl. So the reason women have less blood than men is because they're typically smaller. So this is all based upon size-related phenomena. Blood is also, what you don't realize it, blood is encased in a closed system. And it's hard for you to realize that it's in an enclosed system because you think of all the oxygen our cells need from blood. So how do our cells get the oxygen from our red blood cells? You would think that they would come into contact. They never come into contact under ordinary circumstances. That's why I say it's a closed system. So we will be discussing a system in which the nutrients from our bloodstream pass across the walls of our blood vessels into the area where our cells live and into the interstitial spaces. We'll be doing that a little bit later on, not with this, but later on. So our blood is in a closed system, and we have a pump called the heart, which is responsible for moving it around. But it has, when you draw blood, you actually pierce the system. And you pierce the system that person was very bad at their blood drawing if you have a big bruise on your arm afterwards, right? Because that means things leaked out of the closed system. So it is contained within all of our blood vessels. So blood is not supposed to be anyplace else. Blood has three main functions: transportation function, regulation functions, and protection functions. Blood transports or moves oxygen around from our air to our cells, carbon dioxide around from our cells back to the air, metabolic waste, so cells excrete, so we got to get the waste from around the cells and take them to the right places for us to get rid of them. Hormones are distributed in the bloodstream, and then nutrients are also distributed in the bloodstream. So transportation or distribution center, that's what blood is for. Regulation, because of our circulatory system, going to a nice warm core out to the more periphery, it helps to maintain our body temperature. Where the muscles are nice and active and creating more heat, the blood gets warmed up and takes it to other parts of the body where we don't have as much activity going on. Blood also helps regulation of pH, helps us to keep that 7.4 pH because it actually has buffering factors. Our blood in itself is a bit of a buffer for pH fluctuations. Our blood also is responsible for our fluid volume and distribution of our fluid. So that's its regulatory functions. Protection, our blood carries in it clotting factors and our white blood cells, which are part of the immune system. So that is traveling around in our bloodstream, even though it's a very small portion of it. It's very important in our overall well-being and survival in this world. Plasma is 55% of the volume of whole blood. 92% of that is water. In our water, we will have electrolytes, so sodium, potassium, chloride, things along that line. Nutrients, glucose, fatty acids, amino acids. Dissolved gases, wastes, hormones. I mean, you just can keep going. We'll stop there. That's enough. 7% of our volume of plasma is actually plasma proteins. I said 8% earlier. Let's stick with 7 to 8% plasma proteins. And most of our plasma proteins is albumin. So albumin gives our viscosity. Albumin itself even acts like a buffer. There are many other things in the blood that actually acts as a buffer, and that's why pH is so easily maintained in its range. The formed elements, cells, and platelets, erythrocytes, are known as red blood cells, and we'll talk about them next time on Tuesday. This looks like a good place to stop.